in data science, struggling with high dimensional data is very common. Okay. And there are techniques to handle such high dimensional data, and they are absolutely necessary to have this in your data science toolkit, because this not only helps you to process the data really quickly, but will also help you to improve the model performance. Okay. Hey everyone, my name is Rishabh Sukija. Welcome to my channel where I try to share the AI and ML concepts in a very, very easy manner. And today we are going to look into the implementation of PCA and LDA in a real world situation. Okay. So the problem that I have taken is the MNIST dataset, which is a handwritten dataset. Okay, you have 0 to 9 digits, which are handwritten, and the idea is basis the pixel intensity, we are able to identify which digit it is. Okay, so in an essence, it is a multi-classification problem. So here the classes are going to be 10, 0 to 9, but each of this is an image, which is a 28 by 28 image. And let's see how we apply PC and LDA here. And let's see if we are able to improve the performance. Let's import the libraries first. And we are going to import nb.lib as PLD, and then TensorFlow.class.datasets. So I'm using the keras for importing this dataset, which is the MNIST dataset that we have. Okay. And we don't need this other things, and this should be from, okay, TensorFlow, keras, and I am going to import the PCA, LDA, standard scalar, trains that. Okay, that is also good, and we don't need this. Instead, we would need the accuracy score. We would need the accuracy score, and we will also import C bond as XLS. And from time, import time, and import warnings, and we are going to say warnings.filter.ignore. We are going to load the data from keras. And how do you do that is you would want an X train, comma Y train. This will be in a tuple, and then X test and Y test. We do this and load this in. Okay. So once you have done this, let's try to explore the data a bit. Let's see what all does it have with us. Data exploration. What are we talking about on this? So here, what do we have is we have 60,000 images. This first one is telling you how many images do you have. You have 60,000 images, and each image is 28 by 28. Each image is 28 by 28. And your target is nothing but the Y value, the digit. It is telling you which digit it is. Okay. And similarly, in keras, we are able to load this already into test and train. It has made easy for us, but we are not going to do this since dealing with 60,000 images. And Rose is going to be little, more for the video. So we are going to take a sample out of this, and we are going to look at the implementation. Okay, but yes, this is the exploration that you can do. Let's also do one more thing. Whenever you get the data, try to do basic EDA on it. Try to understand what the data is all about. So what I'm going to do is I'm going to print out the unique labels, like how many zeros are there, how many ones are there, and so on. Okay, let's look at this unique uh, labels and their counts. So I'm going to say labels, comma, and always try to, keep your variable name very intuitive, very intuitive. This will help you. Anyone who is reading your code will be able to understand what you've written. Okay, in real world, in practice, this is very much a skill which is, overlooked, along with the comments. If you're not commenting out properly and you're not using your variables in a really intuitive manner, you'll face some problems in the real world. So we are going to say this, and let's print this. And also I am going to show you label count. I don't want to do this label count here. I want to print it for all number of samples per label. So if you do this, this, and essentially what I'm going to do is I'm going to do a print of all my labels. Okay, how many zeros are there, how many ones are there, how many twos are there, and so on. Okay, run this. So we have 0 to 9 as we suspected. And how many zeros are there? 0 images. 5,923 images are there for zeros. 6,700 for ones. 5,949 for nines. Okay. And they look pretty even. It's not like, you have images of one particular digit which is way less or way higher. Okay. They are pretty much evenly separated or evenly, there in the data set. Okay, all right. Now let's also visualize original digits, and for that we are going to use PLT dot. Here I'm going to say range in 5. I don't want 25 of them. So I'm going to say PLT dot subplot 1 comma 5, and I need to keep an iterator there, which is this I, this one. And then we are going to do PLT dot image show, and I'm going to use explain I value, okay, 0th, and then I'm going to use the color map to be gray. So this is how the images look like in the data set. Now we've got the feel of the data. Let's proceed. Okay. Next step is we are not going to directly deal with image because we are still into a machine learning. Okay, when we go into deep learning, we can read in this as images, but for this particular tutorial, we'll stick to ML. And since we are going to use KNN, they cannot understand this in a pixel format, and the best way is to flatten your image, meaning 28 columns and 28 rows will be divided into features. So 28 by 28 is 784. So you will have 784 columns for each image. And on the Y, you already have the target variable. The image is corresponding to which digit, what is the label. Okay, so let's flatten this out so that we can deal with the images, flatten the images and combine, train and test. Why I'm combining it? Because I want to take the sample. So that's why I'm trying to, combine it as well. So here what we've done is we will call this as explain flat. Let's call this also as flat, and then I am going to concatenate my X. Let's call this as X there, and this will become capital X, and this will also become flat, and we will also concatenate our Y, which is nothing but mp dot concatenate my Y train and Y test. Okay. So here what I'm doing is I'm converting everything. I'm converting everything into these images. Sorry, not images, but into columns. Okay. Let me show you. X dot shape. This is, see, now you have how much? You have 784 columns. Earlier what you had? Earlier what you had? This was the shape. 60,000 plus 10,000. Since we've combined both of them, this has now become 70,000. And this 28 by 28 is nothing but the pixel information, which has now been flattened out into the columns straight. Okay, let us now go ahead and take a sample for faster processing for this video, but you can go ahead and, stick with the entire 70,000 of it as well. Okay. So I'm going to take n samples is equals to 10,000, and I'm going to say that for my X, I want to select top n samples, top 10,000. And similarly for my Y, I want to select top 1,000. Okay, now if you look at the shape of this again, now your X has only 10,000 digits, 10,000. Okay, we are going to deal with only this. Restricting first 10K rows. Okay, so we are going to deal with only first 10,000 rows. Perfect. So now do what? Split the data. Now we are going to consider that this is how we got the data. Okay, this is how we got the data. Now X is nothing but your main data and Y is nothing but your target variable. Okay, we are going to split the data in X train, then we have Y train and Y test, and we are going to use train test split for this, and we are going to pass in our X and Y, and we are going to use the test size equals to 0.2. Okay, let's also put the random state so that when you guys are practicing it at your end, you are able to replicate these results. So now we have split our data. What is the next step? What's the next step? Next step is to standardize the data. So we are going to use the standard scaler to standardize our independent features. Okay. So that's how we do it. That's how we standardize it. Now, this is where we are going to start implementing our PCA. PCA. Okay. So what we are going to do is we are going to apply PCA to analyze the explained variance ratio with all components. Okay, first we need to analyze how things will work like, and where are we getting the explanation? Okay, we will draw a visualization here after we fit it, and I'll walk you through it. Okay, so let's do one thing. Let's save this as PCA all, and we are going to run it for all of it. And then we are going to say PCA all dot fit on our X train. Okay, now we have our PCA model, which is fitted on our X train. Now what we are going to do is we are going to plot the explained variance. We are going to plot the explained. And how are we going to use that? We are going to use PLT figure, and then we need a cumulative sum, which will give us a cumulative sum of all the PCA PCA components. And now what we are going to do is we are going to plot it. Plot cumulative sum, and then we are also going to put a horizontal line on our plot where y is equals to 0.9, and we are going to say that let the color be red. Let me just type in, I think it will be easier, and we want the line to be a dashed one, and let's call the label to be 90% variance link. Okay. This is some, and then what we are going to do is we are going to put in the X and Y values and the legend, and that should be, let's also put PLD dot grid equals to 2, so that we are able to gauge at our end as well. Okay, so now what we are seeing is we are seeing the number of components here and the cumulative explained variance here. This red line is telling us where is that 90% explained. So it is somewhere less than 200. It is somewhere less than 200. We can also print how many, components it took to reach there. Let's do that. It will be even more intuitive. 90%. And this is nothing but n. Of this. There you go. So it needs 193. It needs 193 components. Okay. Out of 784, imagine the power. Only 193 are used to give you 90% variance. Okay. I'm going to go even further down. Let's try to do something around 60%. Okay. Somewhere around 50 PCA. Let's try to use 50 components and see where do we reach. Okay. Where do we get the accuracy to? Does it help us or not? Okay. Cool. Now let's say PCA with 50 components. To do that, we need to do PCA underscore 50, and I'm going to say PCA, and I'm going to say n underscore components equals to 50. This will give me only 50 components, okay? And the model will be when I do PCA underscore 50 dot, we will also transform it here, and we are also going to do the same thing for a test. Let's save them in different variables. Okay, once we do this, we can now move on to implementing this or going further and using KNN. Okay, but before we do that, I also want to show you, using these 50 components, how is your image looking like. This was the original image, right? This was the original image. Let's see if we use only 50 components rather than 784, how well are we able to reconstruct the image of these digits. Okay, so we are going to say x underscore recon equals to PCA dot 50 dot inverse. Now as I told you earlier, that once you apply the PCA, it is no more capturing that information. It is not a pixel anymore. It is a different dimension. So for you to visualize it and put it into an image, you need to inverse the transformation and convert from principal components to the pixels again. That is why we are using this. Okay. And let's do only for the train period. Need not to do it for the test. And what we can do is next, can plot this can plot this again. 1 to 5, 28 by 28. Color map is gray. And label is this. We can also run this now. You see, how is this looking? It's very distorted. Very, very distorted, right? You're not able to clearly say, what is this coming from? Where is this coming from? Okay. Where is this coming from? We are still not able to say it. Okay. Cool. Cool. Moving ahead. Now what we can do is we can also implement LDA here. Implementing LDA. For LDA equals to linear, linear LDA of comments, and we are going to use only 9 here for the time being, which is n minus 1. We are going to convert our test and train. Okay. Data with PCA, and what I'm going to do is I'm going to get this scatter plot. Yeah, this color map as the rainbow, and then we're not calling it X train PCA, huh? We are calling it that, no? Is it capital X? Yes. It's X. And let's get this. This is how this is how your digits are looking like. This is how your digits are looking like. PCA graph is not very clear. Let me do one thing. Let me add the legend also so that this will become clearer. Let's add the title, but PLD dot legend. Let's put in the digits. Let's try to see this. Okay. See, now you have this legend as well. Let's try to do the same thing with LDA, like we saw in part one. Okay, for all those who've not seen part one of this tutorial, go and watch this. It will be helpful. Over there, I discussed PCA and LDA, only specifically talking about those libraries and how you can get, which all functions can you get in PCA and LDA. Okay. Let's use LDA visualization here. This will change to LDA. This will also become LDA. And let's call this LD1. Let's call this LD2. This is LDA. Let's run this. See, much better, right? Much better. These digits, these zeros, ones, these oranges, they are much well separated compared to PCA. And why is that? Because LDA is going after maximum separability, is going after maximum separability. That is why you are seeing LDA to have much better visualization on 2D compared to a PCA. Okay. All right. So now let's try to do the classification and evaluation. So now what we've done is we have reduced our dimensions. We have reduced our dimensions from 784. We've come down to how many? We have come down to 50 for PC and 9 for LDA. Let's now build a classifier. The end goal was to predict the digits, right? This is the information that we have in columns. Let's try and implement that. We have reduced the dimensions. Now we are going to build our classifier model and we are going to use KNN for that. Okay. Let's print this training and evaluating the KNN classifier with original data. I'm going to show you a comparison between the original data. How will the performance be if you do it with original data? How will the performance be if you do it with PCA with 50 components? And how will the performance be if you do it with LDA? Okay, only 9 components. Let's try and do this. First, we are going to do this with the original data. So in the original data, let's call KNN original and we are going to say it is a neighbors classifier. Let's take class neighbors to be 5. Okay, let's take neighbors to be 5 and this is going to be null and we are going to fit it on X train and the original X train. We are going to fit it on the original X train. Okay, not the PCA or the LDA one. Okay. This is where my predictions are being saved and then I want to calculate my accuracy there. KNN classifier not imported. Let's see, did we miss it? Did we miss it? Yes, we did. Yes, we did miss it. So let's import it here. From SQL on neighbors, this is what I want. And let's print a separator here so that we are able to separate out the results. What I'm going to do is I'm going to now use this. Let this be in capitals. Original data on PCA data. Again, it's going to be the same. Let's call this as KNN PCA. And I'm going to use KNN PCA. Here, we are going to use X-train PCA and Y-train PCA. This is going to be prediction for my PCA, and now we will have to also change, our test here. I think the test is exactly this, the Y column is exactly the same. We haven't done anything there. Okay. So the accuracy for PCA will be Y test and Y pred. Okay. And then we are going to do the same thing for LDA as well. To become LDA, it will also become LDA. Here also we will have LDA, accuracy also LDA, and then my predictions also are supposed to be for LDA. Okay. So after this, we are going to print the results. We are going to print the results here, and let me call this as print results. And what I want to print it is print for my original data. I want to print the X train, so shape, and I want to take first one because it is going to tell me how many columns do I have there. Okay. And I'm going to say these many dimensions were present there. And the accuracy is this. For my PCA, these are the dimensions, and my accuracy is this. Okay. And let's also print another important thing, performance results. Let's also print the memory usage. So here, this n bytes is going to tell you how much of these bytes were saved or utilized by your X train. This n bytes will do that, and this is nothing but converting it into MBs. And this is used to float it to get a round value. So this memory piece will also be crucial. Let's run this. Let's see how is the performance coming up. Performance results. So look at this. Original data with 784 dimensions gives you an accuracy of 91%. Look at PCA. with only 50 dimensions, it is already beating the accuracy of the original data. Okay. LDA with 9 dimensions is giving you 89%. Look at the memory usage. Look at the memory usage here. Original data is taking close to 48 MB and PCA is taking 15 times less than that. Only 3 MB. LDA is even going further down with only 9 components. It is considering only 0.5 MB. So when you're dealing with large data sets, not only data compression, but it can also enhance your performance. But having said that, I would encourage you guys to go back, use this, implement it on your own, try different classifier, try to also look at confusion matrix, other precision recalls for the same models. Okay. And let me know in the comments, were you able to implement this or do you have any doubts? Okay. Bye bye. Cheers.